Can. So you only have A and F. I personally think E is in relation to F. If you have a chemical reaction, two things will happen, right? So your reactants will disappear.
Yeah.
Then your products will increase. Yeah, there is mass against time graph. That means what it measures is the amount of mass that is disappearing. Yeah. So then there is the amount of products appearing, and most of the time they measure the gas that is produced. That's why you always see volume of gas against time graph.
But can you use the mass one for product or must use the other one?
No, mass time, what it do is just measuring disappearance. So what they claim is that the amount of disappearance will show how much reactant is used up
during
the process. So the rate at which reactants are used up, right, tells you how fast the reaction is going.
Okay.
Then how much you measure the rate of product form, that is to show that how fast the products are being produced, which also directly says that is a direct measure of how fast the reaction is. That's why you have these two.
Okay. So it's different now. They look different.
They look different. When you use the setup, right, if you measure mass, right, you will end up measuring A. Unless you want to collect the product. Because mass, right, that means you have to collect the solid product. Then you measure the mass as a product, right? So it's, as the reaction is going on, right, it's ongoing, it's not very possible to collect your product that is solid. But the gaseous product, you can collect all the time because the gas will escape. So you collect the gas that is escaping. You check the volume. But it's impossible for you to, as the reaction is ongoing, right, you take out the solid that is forming. Yeah, so that's why
it's still ongoing, right?
Yeah, so that's why if you want, you ask me whether you can measure the mass of product form, right? Not
really lah.
If you want to use method A, it's not possible lah. Eventually, if you put your reaction vessel on top of an electronic balance, right, then what mass you are measuring is actually the mass of the reactant that disappear. Actually, you're measuring the mass of you're measuring the decrease in the mass.
But if the product is a mass also, wouldn't it balance out?
No, that only happens if there's no gas product.
Okay.
If you have a gas product, then the gas will run away.
Yeah, that's true.
So if your amount of reactant and product, right, you can express in mass, number of moles. You can express the volume of gas produced and concentration of solution. Okay. Then definition.
Oh no. Well, still have inverse proportion.
So your teacher would have removed the inverse proportion sign. Then your teacher will probably just tell you this. But teacher probably never tell you this. Right?
Yeah, don't have.
So equation and the inversely proportional to time, this statement is probably more for the more mathematically inclined people. So speed of reaction is a measure of how fast the reactant is changing into product. You might see other versions of definitions, but I've not seen them ask about speed of reaction definition as in the question, like say part A, define speed of reaction. No, I've not seen that. So I mean, we are quite safe to stick with one definition and know what it is. That is pretty much enough.
Okay.
Yeah. Then they say speed of reaction is inversely proportional to time. And this simply just means, if it's like this, math, okay, right?
Okay, ba.
Like that, speed is inversely proportional to time. So it means that when speed increase, time decrease. So that's why you have the statement say if the reaction is fast, the time is short. Nothing fancy down here.
Yeah.
So you have, yes.
So the mass loss you said just now.
Two common methods to measure speed of reaction: mass loss or amount of product form. So you measure either mass or you measure volume. But there's a catch to mass loss. Certain reactions cannot be measured using mass loss.
Oh, why? Because there's gas?
No, even they have there's a gas escaping, right, you still can use mass loss.
Oh,
There's a catch.
There's a-
Okay. So whether to use mass loss or not is depending on what gas is produced.
oh, what gas? Does it affect like some gas heavier or something?
Yeah, so if you have a carbon dioxide gas that is escaping, right, then you can use mass loss. You can use rate of product form, that is fine. But if it's a metal and acid reaction, the gas produced is hydrogen. So if it's hydrogen, right, if you lose 1 mole of hydrogen gas, it's only 2 grams.
Mhm.
Yeah. If it's 1 mole of hydrogen gas, it's only 2 grams. But our chemical reaction, you will not lose 1 mole of gas, which is 24 dmQF.
Oh,
So that means, right, when we do a metal acid reaction, right, the amount of hydrogen loss, right, is very, very little, like probably 0.01 mole. Then 0.01 mole, you calculate the mass of hydrogen, that's only how much?
oh yeah, it won't really affect, right?
So when you use an electronic balance and you put the reaction vessel there, the amount of hydrogen loss, the mass, right, is very little. So your electronic balance most likely will not catch it. Or even if you catch it, right, sometimes because of wind and all that, the value
Oh.
fluctuates, right, then you might think it's an error.
Yeah.
So you will kind of overlook the fact that hydrogen is lost. Then, so in the end, right, your reaction vessel, you sit down there for 10 hours, right, you see, why the mass is not disappearing? The mass is not moving at all.
Oh, so some
Ah.
mass too small to impact.
Yeah, so in reactions, right, for metal and acid, right, or any reaction that produces a very light gas, right, cannot use mass loss.
Then they use the other one, the product.
The product. Because when the hydrogen appears, right, the gas streams will collect the amount of hydrogen that's being pumped out. So you can clearly see that hydrogen is being formed, and you can measure by the volume of hydrogen formed.
Oh, so it's more clear, I guess.
Yeah, but if you put on mass loss for hydrogen, then you will see that there's nothing happening. You see bubble, that
Yeah,
happen.
that's just it.
Yeah. So in this case, right, so they will have that first 2 graphs that you see just now, the graph that is like this, and the
Yeah.
graph that is like this. Okay, you will plot all these measurements for these two, right, into graphs like this. If you want to know how fast the reaction is, you would measure the gradient.
Oh, the gradient.
So if the gradient is steep, right, then it's a fast reaction. If the gradient is not very steep, then it's a slow reaction.
Okay.
Rate of product formation.
Oh, is this the setup?
Yeah, you see that there, right? These apparatus can be used for reaction of carbonates with acid, reactions of metal with acid. Yeah. Then decomposition of hydrogen peroxide, you will get, I think, oxygen or whatnot. Anyway, these are all gas produced.
Oh, the gas very light also, right?
The carbon dioxide may not be light though, but then it's convenient.
Oh,
You can use this. They tell you can use this. Because if you notice, carbon dioxide is CO2. CO2, I think the MR is how much? 12 plus 30, 40, yeah. Yeah. So
But
if you lose half a mole of it, you'll get 20 grams. If you lose a quarter or mole of it, then you get 10 grams. So the mass loss is quite significant for carbon dioxide.
But measuring by volume is easier.
It's obvious.
Oh, obvious. Okay.
That means you can certain reactions you can choose between product formation and mass loss. But if it's a production of hydrogen gas, right, you will confirm that one, the option of mass loss is confirmed out. But everything else you can use both methods.
Can.
So then you examine graphs.
Looks different than just now that one.
Where got different? Volume of gas produced, right?
But it's like smooth.
Same. It's going upwards like that.
Okay.
Yeah. It only tells you that, the reaction may be at a different rate. Because your graph can look like this, the graph can also look like this, the graph can also look like this.
Or as long as it's going up.
As long as it's going up, that means it's producing something.
Mm.
So carbon dioxide is produced over here. So at the start of the reaction here, right, do you know how to find the gradient of a curve?
No, I don't think so.
Find the tangent.
Oh, then yeah, then I draw tangent then.
Draw tangent at that set point, and then you measure the gradient of the tangent. So it means like this, at A, right, you draw a tangent and then you find the gradient. You see the red lines that I drew, right? It shows you that A has the steepest gradient.
Yeah.
Then you know that the higher the gradient, the steeper the faster the reaction.
So at A is very fast.
A is the fastest out of these 3 points.
Mm.
Then B, right, you see that the gradient drop because the speed of reaction is decreasing. Then finally, right, at C, right, the tangent is horizontal, means the gradient is 0.
Oh.
So the reaction stops. Okay. So later on, they will ask you, please explain why the reaction at B, right, is slower than the reaction at A.
Oh, then use this to explain that.
It depends. Maybe it depends on the question. So if they have already given you this, right? Then you can talk about the gradient and all that. Fine. One. They could also ask you to explain in terms of collision theory.
Collision theory? What's that?
The factors affecting the rate of reaction.
Oh, okay.
So then they ask you, oh, why B and A, right? B is slower than A, then or A is faster than B. Then you have to say, so at B, some of the reactant particles have been used up. So then there is less collisions per unit time. Then so it means less effective collision per unit time. So then the amount of the effective collision reduced means the rate of reaction reduced, that kind of blah 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 blah. Which you see
for
later.
C is like use up already, right?
C is all the reactants has been used up. So reaction stop. Then A is because maybe at A at the start of the reaction there's the highest amount of reactant particles.
Okay.
Then repeat the same process again.
Can.
Yeah, if it's mass loss, it's like this. The mass loss setup, right, is significantly easier to set up than the product formation one.
Yeah. Oh, but the cotton wool is there to stop the gas.
Prevent spills from reaction. So you only have the decrease in mass because of the gas loss.
I see.
Yeah, I know. They always ask this question. What is the purpose of cotton wool? I think I've seen it quite a few times already. They give you part of the reaction, then after that, then they have a setup like this. Then after that, they ask you what is the purpose of the cotton wool.
So it's to prevent spills. Okay.
Legit question. I saw it in my students' paper.
Yeah, they really like to ask like, what's the purpose of this? What's the purpose of that?
Yeah.
Okay. Oh, is this the same one as just now?
This one,
like
this is the mass loss one.
Then the just now graph was for volume.
The downward one, right, is always mass against time. The upward one is volume against time.
Okay.
Basically, you don't have to care too much about the words there. You just need to care about the graph and the gray box.
Gray box or okay.
I mean, that's the gray box is the explanation for the graph.
Yeah.
Then the words down there is just to tell you how to derive the amount of carbon that is released, the mass, the side calculations.
Oh, okay.
Because when you start with the reaction, right, you will put the mass balance and then you put your conical flask with all the chemicals inside and then just show on the balance. So then if you just want the mass of the chemical inside the conical flask, right, you will take the total reading of the balance, right, minus off the conical flask mass.
Oh, okay.
Then after that, then if you want to collect the mass of carbon dioxide, right, you take the mass of content initially, right, minus off the final mass of.
Okay.
Yeah. So that is just how you get the numbers. Then you have the graph. The graph is the very important one down here. This is the initial rate then final down here C. So as time progresses, the mass drops, the gradient decrease. So the gradient decrease from A to C because the reaction slow down.
Okay.
Then of course again they'll ask what happens at C. They ask the kind of
Is
stupid
it the
question.
second point?
C, C. Then the reaction stop lor. Or you
Oh.
can say gradient is 0, reaction stop. Then if they want again with collision theory and whatever, right, then you have to say that all the reactants have been used up. Then A, right? What A
Yeah.
is the fastest, B is slower than A. Then you can talk about the gradient at A is being the steepest, so the reaction is the fastest. Then if they want the collision theory explanation again, right, just use whatever we discussed earlier.
Okay.
Same thing.
Can. Whoa, this one look kind of weird. But it's the same concept. It's
All
just
same lah. You know my slides one is
Oh,
always
looks
the
good.
behind one, and the question is always related to the slides in front.
Okay,
Never have I put anything that's out of line.
What was it? Oh, to prevent the liquid from escaping.
1A, what would have caused the mass loss of the flask?
Oh,
Calcium
the
carbonate.
escape the gas. What does calcium carbonate make?
Now your chemical reaction, the acid bases and salt comes in. Oh no.
Carbon dioxide. So it's the escape of carbon dioxide from the flux.
Yeah. So best to be more specific. So like what you say, if the question is like 2 marks, right, then you have to say the calcium carbonate reacts with hydrochloric acid to produce carbon dioxide and blah blah blah. So the escape of the carbon dioxide, right, would cause the mass loss in the flash.
Okay.
Yeah. Then if it's 1 mark only, right, then you can just say the carbon dioxide is
Escape.
yeah, no lah, it escapes. The mass loss is due to the escape. So depending on how much they want.
Okay.
来了.
Oh, just now I say one, right? Prevent the liquid from escaping.
Prevent the hydrochloric acid from escaping, prevent the chemical from the reaction vessel from escaping.
Whoa.
Describe. When you see the word describe means that question, the answer gonna be a bit long.
Yeah, I don't know how to say though.
Describe how this experimental setup can be used to measure the reaction, right? It's probably something like this, the 1, 2, 3.
1, 2, 3.
But you have to adapt it accordingly. Measure, okay, you can do this, then after that measure the mass of the content at regular time interval, then plot the results, right, with a graph, a mass against time graph. Then what they want the measure the rate of reaction, right? So then finding the gradient from the graph will show the rate of reaction, blah 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 blah.
Oh, that's quite long. The escaping of gas
right?
Yeah.
The speed of reaction is calculated by the total mass loss of flask per unit time taken, which is the gradient of that graph. If you say plot a graph of mass against time, right, then find the gradient of the graph, right, that will be fine also.
Then if you say that, do you need to say that what steeper graph? Steeper gradient means like
no, because they only ask you how to measure the speed of reaction. They did not ask you about the conclusion.
Okay. Oh, but this one speed of how is it calculated by the total mass loss?
That means your mass loss, right, is here, this volume, this mass. Then the time interval is here. So when you calculate, when you have the actual graph, right, you will find this mass and you find the time taken. Then you just use the mass against time.
Oh yeah, okay, I see. So that's what the answer means.
Yeah.
Okay.
Mass loss of flask per unit time taken. Mass
loss
over time. I mean, from here, I'm explaining that phrase, mass loss per unit time. You end up mass loss divided by time.
Whoa, region A is the gradient very steep, so the speed of reaction is the fastest.
So you have state and describe. So state here is this.
Oh, okay.
This is the state answer. Then describe, right, is this. So when you have this kind of question, then you have to make sure that you answer both of them.
Okay. Region B, the gradient is less steep. Or the speed of reaction is slowing down.
So it's slower than A.
Yeah, slower than A.
Yeah. So then C.
Does it count as like one straight line?
Yeah.
So there's like no gradient because it's straight line.
Gradient is 0. So you have a horizontal line.
Yeah.
Yeah. So that means the rate of reaction is 0.
Yeah. Because the reaction no more.
Stop.
Okay.
There's no rate of gas.
How do I know? Does that, oh, what? But
This
does
is
that,
for the next part one.
I thought it
So-
would depend on the experiment.
Yeah, depend on the experiment lor. So you change the variables, you can change the surface area, you can change the concentration of the reaction, the reactant.
Oh, okay.
Yeah. Then so it's calcium carbonate and hydrochloric acid. So later on you will see that there is a surface area, there's concentration, there's temperature, there's pressure, there's the catalyst. You might not know about catalyst. So yeah.
There's a lot of stuff. Then it's all related to this also.
Yeah. So if you have those things, right? So pressure, you cannot use pressure here because the reactants, right, are not in gaseous form. Pressure only affect gases. So in this case, the reactants are all solids and liquids, so pressure cannot be used. So
But
you
then
can only
product
use.
is gas. Also cannot.
Which one?
The product is gas, but
Cannot. Your reactant is not gas. Your
Okay.
reactant is not gas. So in this case, you can only use surface area and concentration. Temperature you can use. That means you can say raise the temperature of the reaction.
you like increase the speed maybe.
Yeah, temperature increase will increase speed. Then you can use catalyst, but I think catalyst is not within the syllabus. So bye-bye. No catalyst. Yeah.
Oh, good job.
No, this is the mass loss. This one, right, is the mass of the flask.
Mass of the flask. So mass loss is kind of like the volume loss.
The mass loss increase or not. So down here, mass loss is 0. So down here, this is maybe 100, and then this is probably 90.
Yeah.
So mass loss here is 10. Then say when it comes to here, right, the volume is 50. Yeah, put 60. So the mass loss here is 40. So then at here, right, there's 100, and then down here is 8, say 20. So the mass loss here is 80.
Yeah.
Then here is still 20, so mass loss is 80. So when your graph, right, you draw, right, mass loss and mass of reactive vessel is different. Mass loss is like this. So at first it's 0, then after that mass loss increased by 10, then after that 40, then 80, whatever you call it, then after that it comes across like that.
Okay.
So you draw a graph to show the loss in mass.
Going up, right?
You see, there's a 80 down here.
Oh, I didn't.
Okay, here,
80.
reaction stops at 80.
Oh, okay.
That means the horizontal line starts at 80.
So I need to stop like here.
Yeah.
But this is kind of hard to.
Agak only.
This
Okay,
part look.
I assume behind is a horizontal line.
Okay, so it's just like that.
Yeah, so that is why the answer is like that.
Okay. Wow, chemical reaction.
This is another situation why you cannot use mass loss.
Because there's no gas, right?
Yes. Okay, if there's no gas, right, the total mass of product and the total mass of reactant will be equal.
Oh, so it won't affect because nothing can escape.
Yeah, so if nothing escape, the mass will always be the same.
Okay. Oh, that's a longer explanation than I thought.
It's just being long-winded only. The reaction does not produce any gas, so there's no air gas escaping from the flask to cause the mass loss. They explain, so you have to make sure that whoever who is reading this, right, know what is going on. So you have to be more clearer. What is this?
Calculate after 1 minute. So like at 1 minute. Wow, that's really not straight. But I think it's 40, right? It's like here. Okay.
40 divided by 1.
40 divided by 1 is 40.
Because the formula down here given to you already, right? It says speed equals to volume over time.
Okay. After 5 minutes. 90 divided by 5. 18. Yeah, okay.
Hence describe the speed of reaction from 1 minute to 5 minutes.
Does it increase or decrease?
You tell me. You got the numbers, what?
Because 40 to 18, the speed of reaction decreases as the time something, as the reaction progresses. Okay. How do I know?
Excess zinc is added to a fixed volume of hydrochloric acid. Who is limiting?
Limiting is the acid, right?
Yeah. So that means if you want half the acid reacted, right, means half the volume of gas will be produced.
So it produced 100. So at 50 it looks like 2.
1.5.
Oh, it's
But
fine.
it's just go to 50, draw horizontal line. Then after that, then from there,
I guess, yeah.
like that method is correct.
Okay. Just in exam, use ruler better.
Yeah.
Okay.
Don't eye power all your way down. No eye power, please.
Okay. State and explain the reaction. There's no reaction, right? The thing stopped. Oh, then I need to explain. It's because the reactant has been used up.
Possible. Gradient. Okay, so state of the reaction stop because the gradient is 0. Then after that, all the hydrochloric acid has been used up. Not zinc used up, right?
No, not zinc. It's the acid used up.
So it's the acid. So the answer here, right, could be improved by saying the reaction stop because the hydrochloric acid has been used up, has fully reacted.
Oh, okay.